Transformers' secret sauce, self-attention and multi-head attention. Why we need this? So picture a world where a machine can effortlessly understand the intricacies of human language, grasping the relations between the words and phrases just as the human does. And this remarkable ability is made possible by a remarkable technique called self-attention. But that's not all. Multi-head attention has taken self-attention to the new heights, unlocking unparalleled performance in the natural language processing task. So in this video, let's unravel the mysteries of self-attention and multi-head attention, revealing the secret sauce behind some of the most deep learning techniques in NLP today. Let's get started with self-attention. What is self-attention? Self-attention is a technique used in natural language processing and other fields to help algorithm better understand and process large amount of information by identifying the most important parts of a given input sequence. So to understand it in a layman terms, self-attention is like a spotlight that moves along the sentence, highlighting different parts of that sentence to better understand its meaning. For example, consider the sentence, the quick brown fox jumps over the lazy dog. So without self-attention, algorithm might struggle to understand the relations between this different part of sentence. With self-attention, this algorithm can focus on different parts of sentences at different times, allowing it to better understand the relations between the words and phrases. For example, the self-attention mechanism might focus on the words quick and brown to understand the color and speed of the fox. It might then shift its focus to the phrase jumps over to understand the action being performed by the fox. Finally, it might focus on the words the lazy dog to understand the object being jumped over. So this self-attention has particularly been useful in NLP applications such as machine translation, where it allows algorithm to better understand the meaning of sentence in one language and translate them into another language. It's also used in other fields such as computer vision and speech recognition. So here also with the self-attention, the algorithm will focus on these words hello, how are you. So it shall be just like the spotlight which will move along the sentence key. Yeah, we are talking about this you. So how we are asking how they are. So this way it works. The next is the methodology involved in self-attention. This self-attention mechanism is typically used in deep neural networks such as transformer based models. Here is a general overview of this methodology involved. First is the input sequence. So this first step is to represent that input data as a sequence of tokens where each token is a piece of information. For example, in natural language processing, a sequence of tokens might represent a sentence or a document. Then comes the key value and the query vectors. That is, for each token in that input sequence, a set of vectors is generated, a key vector and a value vector and a query vector. So three vectors are generated: key vector, value vector and a query vector. Then comes the attention weight. So the self-attention mechanism will compute attention weights for each token in the input sequence. This attention weight will indicate the importance of each token with respect to the token currently being processed. And this computation of attention weights involves a dot product between the query vector and the key vector, followed by softmax normalization. Then comes the weighted sums there. So this weighted sum is computed using the attention weight. And this weighted sum represents the output of self-attention mechanism for the current token. And we keep on repeating the same. Right, we have a query, key value, we do the dot products, we do the matmul multiplications, and we keep on doing it. Final output. The final output of this self-attention is a sequence of outputs, one for each token in the input sequence. And this output can be further processed by other layers in the neural network such as fully connected layer or convolutional layer. So to summarize this, the self-attention is used in combination with other techniques such as convolutional layers, fully connected layers to build deep neural networks that can process complex input sequences and make predictions based on the relations between the different parts of the input. So to understand its methodology better, let's calculate the self-attention by hand. So here the goal is to convert the 6-dimensional features to 3-dimensional attention weighted features. That is this features in the 6D, that is in oranges, right? We are converting them to the attention weighted features or 3D features in the blue. So let's walk through the process. First, we are given a set of 4 feature vectors, which is in the 6 dimensions because it has the 6 rows there. Then we are given a query, then key and a value here, right? So you will multiply the features X with linear transformations. First with the query, then with the key, then with the value. Okay, to get these things. And self means that both queries and keys are derived from the self or the same set of features. Okay, so they have, if we will check here, so they are taken from the same set of features. So let's get started. Here, if we analyze this one, here the number of rows, number of columns are 6, and number of rows are 6. So we'll do element wise multiplication here. That is 1 1 0 0 0 0 multiplied with 2 0 0 0 2 1, it gives the 2 here. Then we'll multiply this with this part, then we'll get 1 here. Then we will multiply this with this, we will get 0 here. So this way we'll do. The next we will multiply both these matrices, we'll get this matrix here. So that is 0 0 1 0 0 0 is multiplied with 2 0 0 2 1, it gives you 0 here. Then we'll multiply these two matrices, we'll do the element wise multiplication of these two matrices and we get this results, right? Then we will prepare for matrix multiplication. So here you have done the transpose of this key matrix here. That is, it is written the number of in the column say which x 0 to 1 0, right? This 0 to 1 0 is written in this form, 0 to 1 0, right? We have just done its transpose here. Now we will multiply this transpose with this q vector. Like here we have taken this, it's this is taken as it is, and the transpose of this matrix is taken. Okay, we have taken the transpose of this matrix and this matrix is taken same way. Now we will do the multiplication of both these matrices. As the number of rows are 3 here, the number of columns are 3 here, so we'll do the element wise multiplication. That is 203 multiplied by 001 gives the 3 here, because 2 into 0, 0 into 0 plus 3 into 1, it's 3 here, right? Then that is, we are here, we are doing the dot product between every pair of query and key vectors, and the purpose is to use dot product as an estimate of matching score between every key value pairs. And this estimate makes sense because dot product is the numerator of cosine similarity between the two vectors. Next comes the scale. So here we will scale each element by the square root of dk, which is the dimension of key vectors, right? So dimension of the key vectors is 3 here. So the purpose is to normalize the impact of dk on matching scores. To simplify this, we will approximate this by square root of 3 or with the floor by 2. So here we have taken this, we have simply divided this by 2 here. Okay, so when we will say 3 divided by 2, 1.5, but we will take it 1 here. So 1 divided by 2, 0.5, so it will take 0 here. So 2 divided by 2, it's 1 here. So this way we have done. Then comes a softmax here, that is raise e to the power of the number in each cell. And to simplify hand calculations, we'll take it as a 3 key power. So 3 key power 1 is 3 here, 3 key power 2 is 9 here, 3 key power 0 is 1 here, 3 key power 1 is 3 here. And then we'll take the summations, 3 plus 9 plus 1 plus 3, it's 16 here, right? And next we'll take a softmax, that is for each column you will divide each element by the column sum. The purpose is normalize each column so that the numbers sum to 1. In other words, each column is probability distribution of attention and we have 4 of them. The result is the attention weight matrix in yellow here. So here 3 divided by 16, it shall come out to the 0.2. 1 divided by 6.2. This way we have done. And then we will do the matrix multiplication. That is, we will multiply the value vectors with the attention weight matrix. And we'll get this results here. The results are the weighted features and they are feed to the position wise feed forward network in the next layer. So here we will multiply this 20, 0, 0, 20 with the 0.2, 0.6, 0, 0.2. It shall come out to the 8 here. Next, we'll discuss its limitations of self-attention. So the self-attention, like any machine learning technique, has its limitations. Some of the limitations include computational complexity. So this self-attention is computationally expensive, especially for long sequences. This is because the attention mechanism needs to compute attention weight for each token in the sequence, which requires a large number of dot products and softmax operations. And this can be a bottleneck in terms of both time and memory complexity. Then comes difficulty in interpreting attention weights. So while self-attention allows algorithm to focus on important parts of input sequence, it can be challenging to interpret the exact meaning of the attention weights. This can make it difficult to understand why the algorithm is making certain prediction or decision. Then lack of long-term dependencies. The self-attention can struggle to capture long-term dependencies in the input sequence, especially when the dependencies span over a large number of tokens. This is because the attention mechanism is designed to focus on most important parts of the input sequence rather than explicitly modeling long-term dependencies. Then difficulty in parallelization. So self-attention can be challenging to parallelize. Especially when the input sequence is long. This is because the attention mechanism needs to compute attention weights for each token in the sequence, which cannot be parallelized independently. Then over-reliance on relative positions. The self-attention relies heavily on the relative positions of the token in the input sequence. So if the input sequence is shuffled or the order of tokens is changed, the attention mechanism may not perform as well. And these limitations have led to the development of various variants and extension of self-attention such as multi-head attention, which aims to address some of these limitations by introducing multiple attention mechanisms that operate in parallel. So let us understand what this multi-head attention is. So this multi-head attention, it's a variant of self-attention mechanism that aims to address some of the limitations of this original self-attention. And the main idea behind multi-head attention is to perform multiple self-attention in parallel. And each is focusing on different aspects of the input sequence. So in simple terms, multi-head attention is like multiple heads or views of that input sequence, and each of which will focus on different aspects of the input, which allows the model to capture more complex and nuanced relations between the input element. To understand this multi-head attention, let us consider a simple example in the context of natural language processing. Suppose you are building a language model that needs to understand the relations between a words and sentence. So with multi-head attention, you are essentially running multiple attention mechanisms in parallel, each focusing on different aspects of the sentence. For example, one head might focus on the grammatical relations between the words in sentence, while another head might focus on semantic meanings of the words. And by combining the output of different heads, the model can better capture the overall meaning of the sentence. So mathematically, multiple attentions is achieved by performing the following steps. That is, we will split the input, query, key and value vectors in multiple parts. And we'll perform the self-attention independently on each part of this query, key and value vectors. And finally, we will concatenate the output of self-attention mechanisms to produce the final output. So by performing self-attention in parallel on multiple heads, multi-head attention can capture more complex and nuanced relations between the input element, leading to improved performance in many natural language processing tasks. Thank you.